So now we have, let's do, we have two forces. So two forces. Two forces. What's our down force? Our down force is that kid pulling on the spring. That's what Newton laws, Newton's second law is going to say. So I'm going to just call it capital F. We'll put it capital D. This is the kid pulling on the string, or the stretch of the spring. The stretch. How about by the kid? Or the scientist? Mathematician, the physicist. I don't really know, but it's just the stretch by the person. It's just the stretch. How about that? It's the stretch applied to the spring. To the spring. I'll put in parentheses. Okay? So that's this, I'm going to put comma, the down force. This is the downward force. Okay. Let's come back over here. And let's add to our picture of it. So notice that when we did that, I'm going to extend my little blue line. And I'm going to carry it, and let's just keep track of, well, where did we really end? Okay. We were at rest at some distance y0. But now I pulled my spring a new distance. I'm going to just call this distance y. So that's the new stretch that I've applied to my spring. Yeah, I'm not sure if I want to say downward force. But it's not, this is not downward force. This is just the force being applied by the kid. Sorry, this is the stretch applied to the spring by a kid. You know, let's just leave it as that, period. Sorry. But I think that's more precise. It's a little red palette. So now, let's see what are our two forces. We have the force that we applied. So we have the force that was applied. Force applied has to equal the total force that's in the spring. All right, so let's try this. So the force applied, we said it's just the mass of the spring times some acceleration, is equal to, well, what's the total force of the spring? Well, this is where it gets kind of interesting, because some of your force is down and some of the force is up. So we need to keep our directions constant. This force here is in the downward direction. So we need to keep, and remember, acceleration does indicate direction, changes in direction, changes in velocity. So that's in the downward direction. So let's come over here. Now, when I talk about this, do I have any downward force? I do. I have the mass times the acceleration of gravity. That's what brought it down to y0. So I have that, but I also have, in the other direction, I have what? I have a proportionality constant times the total distance stretched. This is a net force. This is the net force in the upward direction. Yeah, this is the net in the spring. It's not just this, because it was already stretched by that. All right, let's clean that up. Yes?
move that, right? Like the two masses up there are the same.
Yes, those are the same masses.
Oh, they are?
I believe so, yeah.
Oh.
Yeah, those are the same masses. Let's clean it up. Let's clean this up. I'm going to distribute K. So I've got M times A is equal to M times G minus K times Y of 0 minus K times Y. Let's do this. We're going to do this. Let Y be a function, be the distance with respect, well, this is going to be close on space, with respect, with respect to time, we use the variable t. Okay, so if y is a function of time, that's how we express our distance, then what we're going to do is we're going to let a, the acceleration, is y double prime. So if you have y as just some function that gives you the distance, its second derivative gives you its acceleration. So let's do some cleanup. Oh, what do we know about mg minus ky naught? They're the same, right? So what does this term become? 0. And so what I'm left with is I'm left with m times y double prime is equal to minus k times y. I'm going to move this over and we write this as m times y double prime plus k times y is equal to 0. This, that's our most basic second order linear differential. And that'll take the rest of our day. We'll put one more term in it, probably in our next class, and that'll take us another 2 weeks. All right, so what does this describe? This describes, I just think there's two things. It describes undamped, or we'll call this for now, unrestricted circular or harmonic motion. There we go. I'm going to have to come all the way back here. What we're going to do the rest of today is we're going to study that equation.
Where's our MEV minus k equal to 0 go again?
Oh, yeah. I just erased it. No. It's because if you have mg is equal to ky, if I was to do a little bit more work here, this is a good question. I could also write this as mg minus ky0. So right here, if we apply that to this little piece here, that just simplifies to 0. Yeah, good question. I know that's a lot to keep track of. Oh yeah. Does anyone, you want me just to leave that up here for a moment if you guys want pictures? I'm going to do that before I erase. That's a lot of work. So go ahead and take some pictures. You can get up out of your seats. That's okay.